Do you want to fine-tune your own model that, for example, acts like Paul Graham and you can get started advice directly from a replica of him? Or do you maybe want to create a model that is capable of generating ASCII art? Well, today I will show you how you can do use cases like this and many others. So welcome to my official guide to fine-tuning LLMs using Unsloth. In this video I compiled everything I've learned in the past year around fine-tuning LLMs, as I noticed a lot of people are interested in this kind of topic, but they don't know where to start. So I structured this video into different sections. The first one is going to be a theoretical section in which I will explain why you should fine-tune LLMs, how large model providers are training their LLMs, and how you can do it yourself. Because I think it's very important to understand this, as in the second part of the video there will be a more practical approach in which I will fine-tune my own LLMs, but it's important to understand the main principles behind fine-tuning, because fine-tuning has a lot to do with experimentation, trying out different settings, so you need to have a basic understanding about what you're actually modifying. So at the beginning of this video you've probably heard about fine-tuning LLMs but are unsure how to do it. You've maybe tried to run a LLM yourself using something like Ollama, but notice that the performance doesn't even come close to GPT-4o, and you don't know what to do because you don't want to pay for GPT-4o tokens, but the local performance isn't good enough. But after this video, I'm sure you will have a good understanding of everything that goes into fine-tuning your own LLMs, and you will be ready to create your own fine-tunes. So I think an important question to ask ourselves is, why even fine-tune our own models? Well, there are many use cases. One of those is, for example, adding new knowledge to the model, as ChatGPT, for example, is trained on a lot of publicly available knowledge, and it might lack information about the field that you actually want to ask questions about or you need help with. I can, for example, imagine if you're working in medical, legal fields that ChatGPT isn't up to date with your specific documentation. Also, for example, manuals about some industrial machines, for example, a machine from ASML to produce GPUs. I don't think ChatGPT is trained on that. Or maybe some company secrets, which of course aren't included in the training data of larger models. Another use case regarding this I could imagine is, for example, you want to have some NPCs in a game you created, but instead of scripting all the dialogue, you want to have an AI generated. So ChatGPT probably isn't useful for that, and you will need to fine-tune a model on knowledge about your game to get good results. Another reason to fine-tune LLMs is to improve its task performance. You can use LLMs for a wide variety of tasks, but the out-of-the-box performance might not be good enough for your use case. And you can also add entirely new use cases to LLMs, such as, for example, generating ASCII art by doing fine-tuning. Another reason, for example, you want to create a more engaging assistant with a fun personality that's interesting to interact with. With fine-tuning, it's, for example, possible to create your own Johnny Silverhand. Another reason is to improve the usability of local models. Local models can be very beneficial if you're concerned about privacy or simply don't want to pay for ChatGPT tokens. Well, with fine-tuning, we can overcome the limitations that these smaller models have. Finally, another thing related to this is that by training our own models, we don't have to follow the guardrails that are implemented with all the larger models. So we can overcome them by training our own models. You might also be wondering, why are we fine-tuning? Why are we making it ourselves so complicated? Let's just write prompts instead. Well, for certain behavior, it's actually very hard to write a good prompt. For example, let's say you want an LLM you want the LLM to draw beautiful ASCII art. Well, just try to write an instruction about what beautiful is. You will see that's almost impossible. Same with, for example, instructing an LLM to be funny. If you do that, the LLM won't be funny at all. So for certain use cases, it's very hard to write an instruction. And the only way to get this behavior into the model is by just fine-tuning on demonstrations of that behavior. For example, routines of your favorite comedian. LLMs also have a limited context size, so your prompt also can't be endless, which is another limitation. Also, just the prompted behavior might not meet the performance requirements that you need, especially with smaller models. These models often don't have state-of-the-art performance right out of the box, so you will have to fine-tune it for your specific use cases. You might also be wondering, what about RAG, Retrieval Augmented Generation? This is a very common use case for LLMs in which we are using them to answer questions about a knowledge base. It's basically a form of automatic prompt construction in which first, when we want to answer a user query, we are first fetching some relevant documents from a knowledge base and then creating a prompt with both the user query, the retrieved documents, and an instruction for the LLM to answer the user question based on the retrieved documents. So, in my opinion, if you have this use case and you want to answer questions about a knowledge base that changes often, RAG is probably the better choice than doing daily fine-tuning on the entire knowledge base. However, you should know the quality of RAG is very dependent on the retrieval process. If the wrong documents are retrieved, your answers are also going to be bad. So in my opinion, the most interesting thing is if you would combine RAG together with fine-tuning. You then use RAG to accommodate to that the knowledge base is frequently changing, and use fine-tuning to make the model learn domain-specific terms, to make it refuse certain questions, to fine-tune on wrongly answered questions so that the performance actually improves over time. You could also use fine-tuning to give the assistant a personality, and it also provides a fallback for if the retrieval process indeed fails. So it's not a question about or RAG or fine-tuning. In my opinion, to get the best results, you can combine both. So before fine-tuning our own LLMs, let's look at how the large model providers are basically training their LLMs. It all starts with a transformer. And a transformer is a specific type of neural network that looks as follows. And with LLMs, at least the text generation only ones, they just contain this write part, which is the decoder part. And this is responsible for predicting next, just completing your prompt by predicting next tokens. And this part of just the decoder in general is first initialized with some random weights. So the performance is of course very bad if you initialize with random weights. So the first step in the training process is called pre-training. And in this step, we are just giving the model the objective to predict the next token on some unstructured data in order to make the model gain language understanding and background knowledge. The dataset used for this is, for example, a training mix that was used with fine-tuning the first Llama model, and you see it contains for a very large part, it was based on just web data that was scraped. It also contained GitHub to gain some background knowledge into coding, some Wikipedia articles, books, some scientific articles. So in general, a wide variety of background knowledge. And what do I mean with unstructured? Let's just look at a sample of the Common Crawl dataset, and you will see it are just information as it's found on the web page itself. It's probably cleaned a bit, and some personal information is going to be blurred out, but it's just unstructured, so it's not like there is a answer and question or something like that is just unstructured text on which the LLM learns how to predict the next token, and by doing this it gains language understanding and background knowledge. Well, but after this step we only have a model that is able to complete text. It's not able to answer questions and is also not very specialized in tasks we often use LLMs for. So that's why also a post-training phase, or there are actually multiple post-training phases, but one of those is supervised fine-tuning. And in this step, we are actually going to collect a data set that demonstrates an intended behavior. And one of these behaviors we want the LLMs to have is, for example, that it needs to learn how to follow instructions, that it needs to learn how to answer questions about a domain, learn how to have conversations, and basically everything you would want an LLM to be good at. For example, in the Llama 3 paper, we can see that it was trained to get better at English questions and answers, to get better at coding, do exams, and many other things. These datasets, of course, depend on your specific use case, but for example, a well-known one is, for example, this alpaca dataset, and it will contain an instruction and an intended output, and by making the LLM train on this, it will learn how to answer instructions. And another thing, for example, is learn the model to have conversations. And for this, for example, for my Paul Graham model, the way that this data set is often structured is in just all kinds of samples where you describe a certain conversation. In this case, you delineate the turn of the user and the assistant. And for example, the user asks, "What's your name?" And I intend my model to say, for example, "My name is Paul Graham," as I'm creating a Paul Graham chatbot. And my dataset just contains a lot of those conversations. And by training on such a dataset, the model will learn to have conversations. After this, or basically not necessarily after this, as the general order of post-training there isn't a right order, but another post-training phase is the model alignment phase, and this is a reinforcement learning phase. The reason that this is done is to make the model better follow human preferences and also make the model safer. So this time the dataset just contains a set of prompts and rejected and preferred assistant responses. So for example, let's take a look at such a dataset, and you will see that it contains a prompt for the assistant, and then an intended response, the chosen response, and a rejected response. Large model providers do this by using human annotators, but you can easily do this yourself by just providing a upvote and downvote button on your answers and collecting a dataset that way. This is done with reinforcement learning methods such as DPO, PPO, and RLOO. If you don't know what those do, just look at Hugging Face or search some information online, but these are just reinforcement learning methods. Another interesting thing you can, for example, see in the Llama 3 paper is that they did multiple rounds of post-training, and they did a supervised fine-tuning phase followed by a DPO phase. So in general, there is no right order to do these two, and Llama 3 was, for example, trained by doing these repeatedly. However, recently a new post-training phase has popped up, and that's also a reinforcement learning phase. And this one is used to create those reasoning models such as O1, and the latest Anthropic model also has inference time reasoning. And the way you create such reasoning models is by not having a data set of chosen and rejected answers, but instead just having a data set like normal, for example, this data set, which contains questions and answers. And then, okay, let's go to dataset. And then we will basically define some reward functions on the answers. One of those reward functions could, for example, be if the model answered the question correctly. Another one is probably if the completion that the model generates for this question contains some reasoning tokens. And by defining good reward functions, we can actually steer the model towards those outputs without actually having to collect demonstrations of, for example, the reasoning behavior, which is very interesting. So just by defining reward functions, the model learns how to reason itself. And the reinforcement learning that does this is GRPO. It's often done for quantitative domains such as science, math, and coding, as it's easy to define reward functions for those and then create a reasoning model. But there's no reason why it's only useful for those type of domains. Maybe you can also do it for storytelling or something like that, but you need to be able to define a reward function. So now you might be wondering, okay, I have some background information about fine-tuning, but how do we actually do this? Because as you can see in the Llama 3 paper, Llama 3 was trained on 16K H100 GPUs. And H100 GPU, as you can see online, it costs around $30,000 if you can even get it, because it's not in stock and it's actually being stockpiled by all the large model providers. I also don't think you have one of those H100s laying around. So what we're actually doing is fine-tuning a QLoRA, which is a very efficient way of fine-tuning LLMs. And research has shown that when used with small high-quality datasets, it can lead to state-of-the-art results, even when using smaller models. So by doing this, it makes fine-tuning possible for mere mortals like us. It combines two concepts. First off, instead of fine-tuning the actual weights of the models, we are fine-tuning low-rank matrices instead. And the benefit of this is immediately visible here. For example, when we multiply these low-rank matrices, we can get a matrix of the same shape as the actual weights of the model, but instead of having to fine-tune 25 weights, we only have to fine-tune 10 weights. So we are, instead of actually fine-tuning the weights of the base model with full fine-tuning, we are instead fine-tuning these small adapters, which consist of low-rank matrices. And also at inference time, these adapters are just put on top the actual weights of the base model. So for example, they are simply summed together, and this way we don't have to optimize the actual base model itself, but can do it with low rank matrices. But that's just LoRa, and QLoRA is actually when we also quantize the base model and for example represent the weights with 4 bits instead of 16 bits. So you probably know this, but with computers, everything is represented in 0 and 1s, so also numbers. So instead of using 16 of those numbers to represent a certain number, we are only using 4. So that's basically 4-bit quantization in a nutshell. And by doing this, the data requirements are actually even lower. So which models should we actually fine-tune if we do so? There are many open source model providers, for example, the Gemma models from Google, the Llama models from Meta. You also have models from Mistral, DeepSeek, some other Chinese models, and some advice I can give you is that there is no single best model, and it all depends probably on your specific use case. All new models also come out all the time, so you will have to experiment a lot. I think the meta models are especially good as a baseline, and they are, for me, one of the first models I always try out, but that's also mainly because they were one of the first to actually open source their models, so I was just used to fine-tuning them. But just pick one of those as your base and experiment a lot with different models. All these models also come in different sizes, but once again, look at this graph, which will look at this table, which will show you how large of a model you can fine-tune. Larger models lead to better results, but of course they still have to fit within your VRAM. The place you find all these models is on Hugging Face, same with a lot of data sets. You can just search for them here. For example, if I search for Llama-3, you will see the Llama models pop up. For some of them, you will need to, for example, this one has been disallowed in the EU, so you need to search a bit. But a lot of people also re-upload models. And if you, for example, go to Unsloth, which is also what we will be using for fine-tuning, you will see that they will re-upload a lot of models. So you can look at here, also do some, find some inspiration, and you will see that there are many different variants being offered. So for all your models, you will probably find them on Hugging Face. So which variant should you choose? If you spend some time on Hugging Face, you will see that there are a lot of variants, even of the same model being offered. Most model providers provide the base model, which is just a model after the pre-training phase is done. So no instruction following or chat can be done with these models, and they require some fine-tuning for downstream usage. Also often the supervised variant, supervised fine-tuned chat or instruct variant is offered. This one is capable of doing chat, for example, without doing any fine-tuning at all. It's getting more common, and there are these multimodal or vision variants, which can also take, besides text and images input. And you will also encounter GGUF variants, and these are for inference use only and are not trainable. So when to use which variant? Well, you want to use the base model if you don't need any chat or instruction following capabilities. For example, in my ASCII generation chatbot, I just use the base model. You will also want to do this if you want to just first off do some pre-training yourself on unstructured text, and then you can still use this later to do some supervised fine-tuning on. In general, if you want to, for example, turn a base model into an instruction or chat model, you will have to have a lot of data. So that's one of the downsides of training a base model. And one of the benefits might also be that because no supervised fine-tuning is done, you can come up with entirely your own chat template. Then the instruction or chat variant is very useful if you want to leverage the supervised fine-tuning that's already being done. So it also works if you don't have a lot of data. However, you will need to make sure that you format your data in the same format that was used when actually the supervised fine-tuning is done. So you can't come up with your own chat template, but that's actually not a big of a problem. The multimodal variant, use it if you need to have vision in your models. And the GGUF for variants, you should never use this when fine-tuning, only when doing inference. However, still, the first time you go on Hugging Face, you will probably be a bit confused, because there is almost no standardization in model names. So let's go over some of them to give you some examples about how you should interpret what's being written here. So this one is about then a Gemma-3 model, which is the latest open source model from Google. It has 4 billion parameters. It is the instruct variant. So supervised fine-tuning has been done on a template and you can use it right out of the box. And you can see here that we are using an image model, so it is multimodal, and it supports both images and text as input. You will also find this model, for example, which is once again Gemma-3, this time the 1 billion parameter model. It's the pre-trained variant, so no supervised fine-tuning has been done, and it's text only. This is another example of Gemma-3, this time 12 billion parameters, and it's the GGUF format, so it's not suitable for fine-tuning but only for inference. Let's look at a meta model. Here you can see this is Llama 3.3, 7 billion parameters. This time it's also the instruct variant, so supervised fine-tuning has been done, but you will see that it's not named this ID like before, but Meta chooses to, for example, write it out. Another thing you can encounter is something like this. It's Llama 3.1, it's 8 billion parameters, it has been, it's the Unsloth variant, but that's nothing, but with Unsloth they just re-upload the model, so this doesn't mean anything. However, it has been fine-tuned, it has been quantized to 4 bits, and as there is no instruct in the title, this is just a pre-trained variant. So many model providers, just if it's the base variant that is just able to do completions and is not supervised fine-tuned, they just leave out the instruct part. So yeah, it's all a bit confusing, but you will get used to it after a while. If you're unsure, look at the paper in which the model is introduced or some information online, because you will find some information about it eventually. So now, we want to fine-tune our own model. We know how we can find open source models to fine-tune. How do we collect and structure our training data? Well, it depends on the task. If you want to do continued pre-training or just fine-tune on completions, you will just have to collect some unstructured training data. For example, for my Paul Graham model, I first did some continued pre-training, and I did this by just providing the model with some essays of Paul Graham and just letting it predict the next token on this. If you're training a chat model, I would recommend you to store your data like this, where you're just storing conversations on which you want to fine-tune your assistant. It just consists of subsequent conversation turns, and each turn consists of a role. A user means that is a question that I intend to ask the assistant, and then you also provide the answer you want the assistant to give, and you collect a large data set of that. And this is the same as how you normally pass your messages to the ChatGPT API, for example, where you also format it in this format. And the way I generated this dataset was actually by leveraging other LLMs. I had one LLM, for example, generate questions. For example here, I prompted it to generate a question for an upcoming interview with the author of this text. And as the text, I then passed the Paul Graham essay, for which it would generate a question. And then I had another LLM to answer this question. He had to pretend to be the author, Paul Graham. I passed the essay, I passed the question about the essay that the other LLM had generated, and I then made this LLM generate the answer. And this way I came up with a data set. I, for example, stored a subset of this data set here. Here. You'll see it's very handy to store this as a JSON-L, and then it just contains conversation turns like this. Of course, a model can't handle JSON data, so before we fine-tune on it, but you will see that later, a chat template is applied to this format, which will just create a string out of it, and delineate the different conversation turns with some special tokens. And all models have some different chat templates, which were then used during supervised fine-tuning of that specific model. For example, for Mistral, the chat template is formatted as follows. It is in a Go templating language, so it might be hard to understand, but you see every conversation starts with the begin of sentence token. It then loops over all the messages and delineates it with some special tokens. You shouldn't really understand or know all of this. You just look it up when you need it. But the thing you need to realize is that because these chat templates are used, you need to be mindful of that when you're using an already supervised fine-tuned model, that you also need to structure your apply the same chat template that was used during their supervised fine-tuning when you're doing your own supervised fine-tuning. So, and for model alignment, as I explained before, you need a data set of prompts and chosen and rejected answers. And to create reasoning models, you need to have a data set with just questions and answers. So how do we know actually fine-tune the model? Well, we are going to do this with Unsloth, as Unsloth actually patches the Hugging Face libraries, which implement, for example, the LoRa fine-tuning to be much more efficient. Also, as I'm also working on a MacBook, I can't fine-tune on my own computer. You can either choose a cloud platform such as Amazon or Google Cloud. If you are working at a company and you want to do it the professional or right way, I would definitely recommend you to set up something with a large cloud platform. But as a hobbyist, I'm often just using free platforms to experiment a bit, such as Google Colab, which offers a free T4 GPU, and Modal, which is also a cloud provider, which provides you with free GPU credits. So in this tutorial, in the practical part, we will be using Google Colab, as this is the easiest to get started with. However, you only get around 2 to 3 hours of GPU usage per day, and also your session can be interrupted at any time. So that's why I also sometimes use Modal. Modal, you probably never heard about it, but it also offers free GPUs. You actually get around, you get $30 of free GPU credits per month, which is very nice, as you can even use different models. For example, let me look at the pricing. Okay, you can even choose to spend your credits on something like an H100 or something that better fits your use case, so you can even train larger models. So for example, this is a script I created to work with Modal, and the thing with Modal is it wants to do some kind of hybrid between using a cloud platform and running code locally. So you have to format your code as a script and tag certain methods to be run on a cloud GPU. However, this requires you to structure your code very weirdly. For example, you can't import all your libraries at the top, because for code that needs to be executed remotely, you need to import them into function. So the code isn't very clean this way, and I don't like to structure my code like this. I just want to be able to push a Docker image of my code and have it entirely executed on their GPUs. However, it's pretty sweet that you can get like $30 in free GPU credits this way. So in the GitHub, which I also put down in the description, I provided some examples about how you can turn your scripts to be model ready. So after training your model, what you now need to do is save the model such that you can run it locally. And this is done with the GGUF format, which is the most popular one. It combines both your tokenizer and your model. So it contains everything that a PC needs in order to be able to run the model, and it is also able to make your model run on CPUs. So you don't need a GPU. You can also run it on your own PC that doesn't have a GPU, or even on my MacBooks. It just works. You can, when creating the GPU, the GGUF, I mean, not the GPU, you have two options. What you want to do with the weights, these LoRa adapter weights you trained. You can either turn both the base model in a GGUF and the adapters in a GGUF separately, and during inference time just put them on top. This also allows you to easily swap out different adapters at inference time, which can also be helpful for certain use cases. However, you can also just first merge the base model with the adapters by just adding the weights together and then turning that merged model in a GGUF instead, so that the weights are actually packed with the model, and which makes it easier to share your specific model with others, I think. Another thing is that you need to probably quantize your GGUF such that it fits within your VRAM. This once again works the same as before, that you will probably want to have a 4-bit quantization. So this one, Q4KM, is probably the most popular one, but you can see of course less quantized will probably lead to a bit better performance, but it also depends on which quantization you used when training. But you see a lot of options are being offered. However, I would recommend you to either use Q4QM, Q8, or if you don't want to quantize anything, just use floating point 16. This quantization and turning in things into GGUF is done with Llama C++, but Unsloth also has compatibility for this, so you don't need to install it yourself, which I will soon show. There are also some Hugging Face spaces which can turn an entire repo in a GGUF. So this way you also don't have to install Llama C++ on your own PC, as if you're not very technical, it can be a bit hard to install, especially if you're using Windows, so it's not necessary. Finally, after we have created our GGUFs, you can use either Ollama or Llama C++ once again to do the inference of the GGUF. Llama C++ is the library where all other inference providers are mainly built on. So even Ollama uses Llama C++ underneath. However, Ollama is much user-friendly to use, so that's why it's also very popular. Ollama also integrates with a lot of good UIs, which I also showed you at the beginning, but I will also show you after fine-tuning our own model that you can use this to have a ChatGPT-like UI for your own local models. So this is it for the theoretical portion. I hope you now have some understanding about everything that goes into fine-tuning a model. So it's time to start and create some models ourselves. Okay, so let's start with the practical portion and fine-tune a local model to generate ASCII art from GETs, like one of my previous videos. And I've prepared this Google Colab notebook, which you can also find in the GitHub repo from the description. This notebook is adapted from the notebooks that Unsloth offers. So if something is broken, just go on their website, because some package versions might be out of date, which is also one of the disadvantages of using Google Colab, that the underlying image under which which is used as a background of these Google Colab notebooks can actually change dependencies, or the hardware being used can also change, which causes dependencies to break. So to get up to date, just look at the Unsloth website. Also make sure to check that a T4 GPU is being used, because else fine-tuning isn't going to work. I'm going to fine-tune the Llama 3.2 3 billion parameter model, and as you can see, I'm not loading the model in 4-bit, so I'm actually not doing a QLoRA, I'm just doing a regular LoRa. Why would I do that after explaining that QLoRA is so nice? Well, for ASCII generation, I've noticed that quantization actually had a bad impact on the results. The reason being that we first quantized the model right here when training on Google Colab with Unsloth, but after training we want to turn the model in a GGUF for local use, but in that step also a 4-bit quantization is used, but this 4-bit quantization is a bit different from the quantization that is used when training, so I noticed that disturbed the ASCII generation capabilities. However, for most use cases this isn't an issue, but for something as precise as ASCII generation, where even one character can mess up the results, I saw a dramatic decrease in capabilities. So that's why we're actually doing just a LoRa. And if you look online, let's go to Hugging Face, to the model, you will see that Llama 3.23 billion takes around 6 gigabytes in VRAM just to load the model in, so it fits in within the 12 gigabytes that's available on this T4 GPU. So sometimes training a LoRa without any quantization with a smaller model that fits within your memory might actually outperform a quantization of a larger model. However, for most use cases, I would just use a QLoRa, and for the next example, I will also be using a QLoRa, but just be mindful of that, and that's the reason why I'm not loading it in as 4 bits right here. Something else, on Hugging Face, when you go to the model, you can actually inspect what's inside it, which can be a bit interesting to look at. You see that the model contains multiple different modules or layers, and these layers have a certain precision. So when quantizing, we are basically just lowering this precision. Okay, the model has been loaded in together with the tokenizer. The tokenizer of Llama actually contains something weird, or it's not weird, it just cleaned up some spaces, which normally isn't an issue, but when generating ASCII art it was an issue. But you shouldn't really mind that when training most models. So now we are going to apply the LoRa adapters. And the way this works is we define some target modules, and these are specific layers within the model. For example, we are targeting the cube projection, the K projection, the V projection, and some other specific modules of the model to actually apply the LoRa to. So we are not applying it to all the layers. For example, to the embedding token layer, we are not doing it unless I turn this on, and it's a bit more advanced, but sometimes you actually want to train the embeddings when you're adding new tokens to the model. However, for most use cases this isn't necessary. So now we are adding the LoRa adapters, and this is also where Unsloth will patch the model to make it more efficient. Some parameters that are useful to know is that you can choose the rank of the LoRa matrices, but most of these settings are set to some values that are considered optimal. So of course you can experiment a bit with that, but yeah, it is what it is. Okay, so now we are going to load in our data set, and to do this I prepared an entire data set of ASCII GATs. I scraped these from the internet. They're a bit messed up in this viewer, but yeah, they're actually formatted correctly. All your datasets should be stored on Hugging Face, and you can easily add a new dataset by creating it like this. The way I created this dataset was actually by I store all my cats in a text format, and I basically create a pandas data frame from this with as columns the ASCII art, and the creature is just a cat. Yeah, I don't really do anything with the creature column. I turn it into a data frame. I store it to a Parquet file, and then this Parquet file you can just put on Hugging Face. So now we need to prepare our data set for use with, we need to turn it into a prompt we can use supervised fine-tuning on. So this is done with this function, which first loads in my data set. It takes the train split. We then define a prompt, but in our case the prompt is just the ASCII art itself. We fill it in with the ASCII art we extracted from the dataset we pulled from Hugging Face. We add an end of sentence token, so we know that when the model generates this token, he is done with his completion and we can stop generating. And then we create a dataset by storing everything under a text key. So let's run this code. If you're if you want to do this yourself and want to adapt this, just start from this code. Okay, it timed out weird enough. I've actually never had that happen before. Of course it happens now. Okay, see, now it works. But just adapt this code a bit, and it's actually yeah, it needs to be stored under a text key to work with Unsloth, or yeah, with the Hugging Face libraries, unless you set in something different. But okay, so you will see that we have now formatted our data set like this, which is the ASCII cat and an end of the text token at the end. And the only thing the LLM is doing is starting with an empty token, predicting the next one until it predicts the end of text token, and then we consider that the generation is done. So now we initialize the supervised fine-tuning trainer from Hugging Face. Here we specify this text field so that it knows how to access our training samples. Some other parameters are, yeah, these are just some optimization parameters. It's interesting to look further in them, but it's not essential. Also, the optimizer is an ADAM-W optimizer, which is very common. You can also put in some weights and biases dashboard right here, which is useful for tracking yeah, the training process. But once again, we just are going to do it with a basic setup right now. We are going to train for 3 epochs, so we are going to go 3 times through all the training data. You shouldn't do this too often. You shouldn't train for that many for too many epochs, as you can overfit on your training data, and then your model will just only be able to generate your training data and not generalize well to new examples. So it's recommended to only use 1 to 3 of those epochs. And now just press the trainer train to start training. We will see that we have drastically reduced the amount of parameters we are going to train by using the LoRa. So now the training process is done. I see we went all the way down to a loss of 2 from a loss of around 4. Probably some more training could be done without overfitting, but let's see what we are dealing with right now. We just press it, we just pass it an empty input and just make it generate the next token, because that's also, we didn't define any prompt. So let's generate some ASCII art from the model. Let's see if the cats come out nicely. Okay. They are a bit weird, but we also didn't train for that many epochs. So maybe let's try to improve the performance a bit by training on 2 more epochs. Okay, we trained on 2 more epochs, brought the loss a bit more down. Let's see if the ASCII generation starts to resemble our training set even further. Okay, it seems the model has improved a bit. Of course, it still isn't perfect, but you can see the results are getting better. You also don't want to train on that many epochs, like I said. Like, you don't want to do like even the objective isn't to get the training loss as low as possible, because after a while you will just be generating examples straight from your training set, and the goal is to actually train to get new outputs instead of just creating a dictionary of your training set. So now let's save our LoRa, and for this example I'm not going to merge the weights and the LoRa's and create one GGUF. Instead I will create a GGUF of both the LoRa adapters and a GGUF of the base model, and then put them on top of each other at inference time. So to do this we can just use this function. I will just put test here after it, or tutorial after it, or guide after it, as we are creating a guide. So push it to the hub. This will this will use the Unsloth library to push your LoRa adapter only the LoRa adapter to Hugging Face. You also need to pass your Hugging Face token, so I use a Google Colab secrets for that, but you can also type it out right here if you want. So we can see that our LoRa adapter has been correctly saved. It's saved under my name, it exists here. So to turn it into GGUF, you can either go the hard way and install Llama C++ yourself, which does the quantization. Luckily, Llama C++ also offers some Hugging Face spaces. Let's see if I can find them. GGUF, my repo. Like you can see, GGUF my LoRa. I will also put this in the GitHub repo that I put in the description. Let's first log in here. And what we can then do is just pass our, I think I need to pass this one, or the name of our repo. We then pass the required quantization, but you should not quantize the LoRa adapters themselves. So put this in floating point 32, as this is also the precision or weights are stored in normally, so no quantization, and then submit it. And this actually runs Llama C++ on a server of Hugging Face. It will not take very long, and you will see it has created in our repo a GGUF version of the model, which looks like this, a bit different from our base model, but it's also a different format, and it contains everything that needs to be known about this model. But now we only have a GGUF of our LoRa adapter, and we also need a GGUF of our base model. I also did this previously. I created a GGUF of the Llama 3 base model, but I will quickly show you how I did that, so you can also replicate it yourself. To do this, I actually put a script in my repo under GGUF conversion. You can do this also once again yourself, either with Llama C++, or you can create a Google Colab notebook. However, I also want to demonstrate a bit how modal works. So we are going to run it with modal instead. And what this does is we load in the Llama 3.2 model, and we will load it in. We will basically load it in, and then using Unsloth once again, push it to the hub in GGUF format without using any quantization. So I set quantization method on off, and I also don't load it in 4-bit. We're going to load it in fully, not quantize it and save it as a GGUF to Hugging Face. Okay, the way you run this is first off create a modal account, but just go to the website, once again model.com, log in, create it, and it should be fairly easy. Then I can run this script as follows. Okay, no Docker file found. Okay, I actually need to put it like this, because I pass a Docker file which contains Unsloth to modal to run the code in. You can also follow your training logs right here. As you can see, turning models into a GGUF can take a while. I'm already waiting 5 minutes, and only now we seem to be uploading it to Hugging Face. But the benefit of modal, of course, is that I can just close my computer and the job will continue in the background. It seems that we have successfully turned Llama 3.2 into a GGUF. We can also see it locally, so let's go to my Hugging Face. And indeed, we have a base model in GGUF. So now let's try to run this model locally. To do this, first we need to clone it, of course. So the way you pull models from Hugging Face is very simple. You just click here on clone repo. You need to have git large file system installed, but I already have that. So if you don't install this, else you will just be cloning some metadata, I think. It takes a while because it's of course a 6 GB model. Okay, after some waiting, we see that the model has been cloned. It can be found here. It actually downloads a folder for the model. So what I'm actually going to do is rename this one base Llama 3 guide or something, and put it out of this. Okay. Okay, now we are going to do the same, and with our LoRa adapter. So once again, do git clone, pull it. It's probably going to be a lot faster because it's really small, and I will just call this ASCII LoRa.GGUF, just temporary, of course. Okay, and now there are a couple of ways to do inference on this. For this model, I'm going to show you how you can do it using Python. So let's go to this script, and we will actually be using the Llama C++ Python bindings, which you can install from here. This will allow us to do inference of these models in Python. I'm gonna copy the path to the LoRa right here, and I'm going to put the path to the base Llama 3 model also in there. Then you just specify the base model, the LoRa, the context size, and load it in. So let's take a look at the inference parameters. You can play with this a bit. A higher temperature increases randomness, a lower top P decreases randomness. You can also introduce some penalties. So let's see what we can generate with this. Okay, this does resemble a cat. That one doesn't. Let's see if I can open this. But you see, a lot of generation or quality of generation also has to do with the amount of randomness you allow right here. So however, this reflects what we have been seeing during inference. We also didn't train on that many epochs, But in general, this is the way you can load in your adapters dynamically. A benefit of this is that you can also then easily swap them out. But in general, this is how you train and do inference with a completion model. Let's now train a chat model. Okay, so I quickly went to the gym, and now it's time for our second example, creating a chat model which behaves like Paul Graham. If you don't know Paul Graham, he's a famous essayist. He writes a lot about startups and business. He's also the founder of Y Combinator, one of the most popular startup incubators. So who else would be more ideal to chat about your startup ideas with? So let's try to create some kind of a clone of him. First off, we are once again going to install our dependencies. We are going to load our base model. This time though, I am using a QLoRA. You can see I'm loading it in 4-bit. I'm also using the already 4-bit quantized version. So you don't necessarily have to do it if you just use the regular version and put load in 4-bit to true. You will also train a QLoRA, but this just makes downloading the model a bit faster because you don't need to download a full model. You're already downloading the quantized version. Maybe inspect it. You can see it's only 5.7 gigabytes. And yeah, if you would load the full version, it would take around 16 gigabytes as expected. Okay, I forgot to create a secret for this notebook, so let me quickly do that. Thing you can do it is just here with add new secret. So as you can see, a 16 gigabyte model that is 4-bit quantized actually takes up less storage than a 3 billion parameter model, which shows you a bit the power of quantizing models. Okay, the model has been loaded in. I first want to show you what exactly a chat template does. For example, my dataset is structured like this, and the newest models have an applied chat template in their tokenizer. If you're downloading the instruct model, as I said before, they have been supervised, fine-tuned already on a certain chat template, and you can access it with the applied chat template method of the tokenizer, and it will just convert these messages into a string basically. So now we are once again applying the LoRa adapters. Once again, we are applying it to mainly the attention modules of the model. You can once again, if you want to experiment a bit with this, you can, for example, experiment a bit with the rank of the matrices or with all these different settings. More information can always be found here on the actual Hugging Face page of LoRa. And now we will create a dataset. Let's get our conversations. The dataset actually consists of these conversations that I have generated with the use of AI. As I have shown you before, I am just using a script. Where is it? Here we are just letting LLMs actually generate questions about essays and then having another LLM actually answer that question while pretending to be the author of the essay. And this resulted in this entire data set. So we once again do this, but this time we are actually applying the chat template. Unlike with the completion model where we were just passing in the ASCII art, here we actually have to apply the chat template. Let's visualize some of our data set now. You can see the chat template is correctly applied. And once again, the training objective will just be, we start with the empty, with an empty string, and we start predicting next tokens. And the model just needs to learn how conversations work. So let's train the model. The parameters were the same as before. Let's see, maybe I will just, I'm just gonna train on 5 epochs right from the start. The settings, I'm not doing anything special with the settings. And let's train. See, once again, we are only training less than 1% of the actual trainable parameters of the model. Okay, after 45 minutes, our model has finally trained. We can see we went down from a loss that started at 2, and now we only have a loss of 0.2. So let's see and ask the model a simple question: how to do a startup. And you see, it is pretending to be Paul Graham. It says it can be the most exciting and fulfilling thing you ever do. So how do you do it? First, you need to be one of the movers and shakers, blah, blah, blah. It seems that the fine-tune worked correctly. So how it works is, first, you once again pass a message like this. This is then formatted using the same chat template as before. And then the LLM will simply, with the LoRa adapters applied, know how to complete the role of the assistant. So he knows, because he sees this, that he now needs to start generating the part of the assistant, and he does it correctly. But so we trained our model, and now we want to run this locally. But this time we're not just going to save the LoRa adapter separately. Instead, I will show you how you can actually merge the LoRa adapter into one model with the base model and then save that model to GGUF. And you can do that with this method. And then we are going to use the 4-bit quantization that GGUF offers, and then just call the push to hub GGUF method of Unsloth, which will then in the backend just call Llama C++ to do it for us, but it's very convenient that they offer a helper function for this. So now we just have to wait until the model appears under this name in our Hugging Face repository. It's gonna take a while, so once again, we need to wait a bit. Okay, I think almost 40 minutes or at least half an hour later, and our model is finally merged. So always check that you have enough usage on Google Colab, and if not, just switch to model, because everything like this takes a lot of time. So you don't want your Google Colab instance to get shut down when you're in the middle of saving your model. But let's see, it seems to have been correctly put on Hugging Face. So now what I will try to do is show you how you can run this model then locally with Ollama. Okay, so now let's show you how you can run this model that we trained locally. First off, I'm gonna create an additional folder here called Paul Graham model. I'm going to go into this folder, and we're once again gonna fetch it from Hugging Face. Okay, it's stored right here. In the meantime that we're downloading this, we are going to be using Ollama. This is very easy to install, just follow the installation for your specific platform. Ollama is, by the way, very helpful for finding new models and running them easily. You can just copy the command, go to your terminal and paste it, and the model will get downloaded in the background. Often the Q4KM variants are used, which we also use to quantize or GGUF. Okay, we have fetched the model. Let me once again go into it. What we're going to do, I'm going to call this, just to make it a bit easier, Paul Graham model, and then I'm going to delete this folder. before we move on to Ollama, let me just show you something else very quick. We can also once again use Llama C++ to do inference with also on chat models with a GGUF. Let me go into it. This time we just paste this model, we load it, and then we can just create a chat completion, which you should, it's very similar to how you call an OpenAI model. So let's see if it says, normally it should say I'm Paul Graham or something similar like that. It says I'm Paul Graham, a venture capitalist. So if you want to program, want to implement your local models, and you want to program against them, you should definitely consider using the Llama C++ Python library. But I also want to show you how you can interact with it in a user-friendly way. So the first step is downloading Ollama, which we already did. And now we should just add our model to Ollama. I added some instructions about how we can do this. First, you need to create a model file. So I've created a blank model file, which we need to set up with our own model. So we need to configure it for our Llama 3.1 model. First off, the from should point to the GGUF of the model we want to add. So just copy the path to the model. I think it has to be a relative path. So this should work. Paul Graham model. Then we need to set the chat template. I just went on Ollama to the 3.1 model, and when you click on template, you can get the Ollama chat template for this. So I'm just gonna copy it. Okay, then we need the stop token, and we have for our chat template, this was this EOT token. I think it's end of something token idea. So let's put that one right there. And then we also need, importantly, the system prompt that was used in the chat template, and that is just this portion. So you can see that is what's put inside the system role. So this also depends a lot on the chat template that you're using, and you can easily retrieve it by printing out your dataset in your notebook. So let's put that one right there, and let's see if it works. Now we can create or add our model to Ollama by just going to the model file and typing Ollama, create the name of your model. I'm just going to call it Paul Graham Guide model, and then point to the model file. Model file, I named it model file Llama 3.1. Let's see what this does. If it works at all, it should tell you. Okay, it seemed to have loaded in the model. Let's check if it works. You can type Ollama list to get all your models. I can see that this one is added. And now we can just type Ollama, first let's do clear, Ollama run our model. It will load in the model on our CPU. We can also see here on top that it's working. Okay, let's see if it actually loads. It's loaded in. Let's send a message. Who are you? Okay, and it's correctly saying introducing himself, but it isn't very nice to chat through the terminal, so we are gonna set up a nicer UI right now. And I think the best UI is Open Web UI, as it really resembles the OpenAI UI, and it also integrates really well with Ollama, which is also one of the reasons why I prefer, for use cases like this, when I want to manually chat with the program and not through an API, I prefer Ollama over Llama C++ because Ollama integrates nicely with UIs like this. To install it, you can either use a pip, but personally I like to do it with Docker, as that's easier for me and I don't pollute my virtual Python environment. I am not going to give an entire Docker tutorial, so let's just say first download Docker on your PC and then just execute this command. I've already okay, let's open Docker. I've already downloaded the OpenWeb UI. Okay, it seems to have started. Let's go to our local host. We can see that the UI has opened up and that is pretty clean. And our model should appear right here. Paul Graham guide model. Let's type a message. Can you help me get good startup ideas? And it correctly says that you should identify a problem you care about. You'll be surprised that the best things come from trying to solve your own problems. Really good advice. That's also present in all his essays. Help me come up with an idea. And it gives you an idea for a platform that helps optimize energy consumption at home. I think this use case is very interesting because you can actually, by doing this, chat with the author of the essays or books you enjoy reading. So this is it for the Paul Graham model. Okay, and now last but not least, let's take a look at how we can create our own reasoning model similar to the O1 models of OpenAI. And to do this, once again, we will be using Unsloth. We are first going to install the requirements. These are a bit different. You should also, once again, if the notebook isn't working, go to Unsloth, the website, because they have lots of notebooks that demonstrate GRPO reasoning. GRPO is also the one that I have the least amount of experience with, as it's the newest. Okay, so our requirements are installed. Now let's load our model similar as before. We will be using a Quen model just for some variation. I'm also using the 3 billion parameter model and still quantizing it because training a GRPO requires a lot more memory, because underneath, if you actually look at the GRPO algorithm, a lot of completions are generated at each turn of the reinforcement learning. Okay, so now let's look at the actual data set, how we prepare it, and what sort of reward functions we define. First off, we define a system prompt. So here we give instructions to the model that it should respond first off with a reasoning process between reasoning tokens, and it should output its final answer between these answer tokens. We then load in the dataset. It's this OpenAI dataset we are using, which just contains some questions where the model has to do some calculations. We load in this dataset and then we construct our own dataset based on this, because we have to do some pre-processing to create a dataset in the right format for it to be used with GRPO. And GRPO basically requires for every item that there is a prompt and an answer, and the prompt is basically a conversation like we defined with our previous model. So the conversation just contains the system prompt as the system message and the question from our dataset. So we just parse all the questions from this, and the answer, we extract the answer from the dataset. And as you can see in the dataset, the answer is put after these 4 hashtags. So we just parse these numbers out of the dataset, and after this function, we basically have our entire dataset pre-processed in the right format. Okay, we then define some reward functions. The reward functions are mainly about checking if the answer is correct and then giving it some reward. There's also another int reward function. I think what does it do exactly? It extracts the answer once again and just checks if it's a digit or not. So if it's a digit, an additional reward is being given. We also give rewards if the output of the model follows the template we have defined. And we also additionally give some rewards if the right tokens are included. I did not define these reward functions myself. It's something that this researcher has basically developed for us, and it seems to be working very well in order to get to train reasoning models. So that's also why we are using it. So after defining this, let me load it. We are then going to set up a GRPO config. Once again, you can experiment with all these parameters. If you want to know what they actually mean, go on Hugging Face and look them up. We then define our GRPO trainer, which contains our model together with our reward functions. And we start training. Once again, we are only training 2% of the parameters. However, I'm training on, 250 steps, so 250 gradient updates. This is different from epochs, but we are not trying to train a perfect model. I just want to see if after 250 gradient updates, the output of the model starts to reflect what we are expecting. So yeah, now we just need to wait and see if after a while the model learns what we expect it to learn. Okay, after training for 1.5 hours, we can see that it's finally done. We trained for 250 steps, and we should see that the reward he receives at each step should go up. So at first it's indeed a lot of the rewards are negative, but hopefully at the end, as we can see, he learned how to get rewards, so his completions should have gotten better. For example, also if we look at the correctness reward, we see at the beginning there are lots of zeros, but at the end we can see more twos. So indeed, it seemed like he should have learned how to reason, but now let's do some inference. Okay, so first we are going to, for example, ask how many R's are in strawberry, the classical question, and see what he answers before I applied the LoRa. He says there are no letters R in strawberry. Okay, and I typed it wrong. Okay, strawberry instead of strawberry. Let's see if he answers it now. There are no letters R in strawberry. Okay, and let's now see what the reasoning model does. First, save the LoRa and load it. So now let's ask the exact same question. Hopefully he now gives the correct answer, or at least tries to give an answer. Okay, he indeed tries to reason. Wait, I'm gonna print the output, maybe that will make it a bit clearer. Okay, he indeed correctly outputs reasoning tokens to find the number of R's. I will go through them by character. Indeed, and he correctly finds that there are 3 R's in strawberry. So you can see that our reasoning model seems to be working, or at least way better than before training the LoRa. So note that I've showed you everything that I know about fine-tuning LLMs. I hope you have now gained a better understanding in this topic, and feel confident in trying to fine-tune your own model. I'm definitely looking forward to seeing what you guys come up with, so leave down in the comments below if you did a fine-tune, and also definitely if something is unclear, just leave a comment and I will try to help you. So I hope you enjoyed the video, and I hope I see you in the next one.